Chapter 27, Theory Video 2. We are going to discuss power and alternating current. So now we know that electricity carries power. When alternating current passes through, we know that the current and voltage are also varying. Then how about power? Power should also then dip and increase at the same rate in a similar manner. Then why can't we see the lights to be flickering? We can actually see the flickering, but they are adjusted in such a way that we cannot notice it that much. That is, if you take a filament light, it cools down, but the cooling down is positive and negative, change of power makes it cool down, but that cool down is the time for the cool down is so slow that it doesn't really it doesn't have time to cool down uh, so that we can notice. Then the relationship between the peak value VO of an alternating current and a direct voltage that would give the same average electrical power is what we refer to as the root mean square. That relationship, then we can calculate that the direct voltage is about 70% of that VO. That is, the direct voltage is about 70% of the peak value of the alternating current. So that means if uh, the voltage of the alternating current is at this point, right, then the direct current that would supply the same thing should be, the voltage is somewhere here, but we have to be, in a general sense it should be at the halfway point. But why is it not at the halfway point? It is not at the halfway point uh, because please give me one moment to clear this. um, because of the shape of the graph, because of the sine graph, we don't get it to be 50%. So we have it about 70%, and mathematically we can prove that, which is called the root mean square of the alternating current, which is going to be equal to the direct voltage that would be supplied. So this voltage, the steady direct voltage that gives the uh, same average voltage as VO, is referred to as root mean square value of the alternating voltage. Then in the same way we can figure out the root mean square value of the alternating current as well. Now the equation for these two, IRMS, root mean square of the current, in relation to the IO, or the peak value, is that is the root mean square value of IO, that is the direct current that would be required to give the same alternating voltage, um, is calculated by IRMS equals IO upon root 2, which would give us 0.707 into IO. So that is the relationship, 0.707. That is where we get the 70% mark. It is you must remember that it applies only to sinusoidal alternating currents as well as alternating voltages. IRMS equals IO upon root 2, then VRMS equals VO upon root 2. Then the root mean square values are these, IO upon root 2, and gives you 0.707 into IO and 0.707 into VO. Write down a note on this. When alternating current provides electricity, not only the current and voltage varies with time, but also power varies with time. leave a line and write the relationship between the peak value VO of the alternating voltage and a direct voltage that delivers the same average electrical power is defined as the root mean square value RMS value of the alternating voltage. That is let's say alternating voltage has 100 volts, then the direct current should have a 70 volt power, 70 volt voltage to provide the same power. That is what it means. This value stands at around 70% as proven mathematically. 70% of the 70% of VO proven mathematically, and would have the same relationship with the mean square value of alternating current as well. And then write down root mean square value of IRMS equals IO upon root 2, which is equal to 0.707 into IO, and IO peak maximum current IO is the maximum current, then VRMS equals VO upon root 2, which is equal to 0.707 into VO. It is going to be the maximum voltage. Now we are moving into practical activity 27.2. So here what we are going to do is we are going to practically see how this relationship stands. Now the power supplied by an alternating AC current is always changing. So we have to have some sort of average power to do our calculations and to figure out what sort of how the machinery can be powered by these things. Then what we do is we compare this alternating current with a direct current, and we find out how much power would be supplied by a direct current as similar to the alternating current that would provide the same power. So what we do is we have two filament lamps, we call them resistive loads, placed on either side. One is connected to AC and the other one to DC. So the AC is adjusted in a way that both of them are equally bright. So that means they would provide the same average power. So then what we do is we compare the output voltages on a double beam oscilloscope. So this will, it will give us now the line here. This line here gives that gives the value of DC, but as you can see, AC goes above that, so that shows that it should be higher. So the AC is delivering more power than DC, and DC is at a regular rate as shown here. So this is the DC power and this is the AC power. I hope it makes sense. So now you understand from what happens to that why it is 70%. Write down AC and DC power supply can be compared by using two resistive loads within brackets, example filament bulbs, which are supplied with AC and DC current in such a way that both would have the same brightness. Output voltages are then compared on a double beam oscilloscope, which would give us a reading as follows. And please draw this, then you would be able to understand what it means. Leave a line and write after drawing. The AC sinusoidal curve would suggest that it provides more energy sometimes than the DC power. Right. I hope that you have understood. If you have understood, please do question number 7 and 8. We are going to discuss about how to calculate power. Now, we have used the RMS values. So we can use these RMS values to apply in equations, and we relate it to direct current equations. So if you have an average power, we can use those values to DC equations. So now if you want to find out the average power dissipated in a resistor, so if we know the mean square values, then we can figure out how they relate. So the equations for power, P equals I squared upon R, then P equals IV, and P equals V squared upon R. So these equations we can use in calculating the values related to alternating current. So we have to use RMS values, that is the root mean square values of current and voltage, as we are going to calculate in this worked example. But if we use the peak values instead of RMS values, the answer is going to be a factor of 2. Not, that 70% relationship is not what we are going to take here, because we are going to take the square of that. Now IO is equal to root 2 IRMS, that is what we had. So if we use I squared R, then what happens? Here we have I squared R. We have I squared R here. So when we square it, what will happen? That root 2 to square will get cancelled out, and as a result we will have root 2 to the power 2 is 2, so it would have a power of 2. So for the voltage also the same thing, it is a power square V squared upon R. So then that is also going to be an issue for us. So we have to make sure that it is not VO, it is VRMS that we need to use. So now let's look at this worked example. A 20 ohm resistor is connected to an alternating supply. The voltage across the resistor has a peak value of 25 volts. Calculate the average power dissipated in the resistor. So first of all, what we need to do is we have to find VRMS. We know that it is VO upon root 2. 25 upon root 2 is 17.7 volts. That is 70%. So then to find out the average power dissipated, again we use the RMS value and not the peak value. So we use V squared is 17.7 squared divided by R is 20, we get 15.6 watts. So if we had used VO instead of VRMS, we would have gotten 31.3, which is double the correct answer. So I hope you understood. If you have understood, do question number 9 and 10. Then, but before that, let's write down this note. To calculate power, using the average power values that we have obtained, we can use the direct current equations. P equals I squared R equals IV equals V squared upon R. Leave a line, put a star and write down. However, we must use the RMS values of I and V. If we used VO values, that is the peak values, we would get double the correct answer. I hope that makes sense. So please do questions 9 and 10. Now, to explain the root mean square, we need to take these details. Here, now we need to understand how the root mean square is applicable, and how this equation IO equals root 2 IRMS comes about. We know that power equals I squared upon R shows that, it will show that the current has a direct relationship with power. That means the current squared is directly proportional to the power. That, in other words, power is directly proportional to the square of the current I. So now when we look at this, here when we look at this chart, we are looking at an alternating current. This is going to be positive and negative. However, if you take I squared, it is always positive. It is always positive. Now, as you can see here, let's try to make sense of this. Now at this point, so this is the current against time graph. This is the 0 value. So if you bring this down, the square of that is 0 squared is 0. This value, when you square it, it is always a higher point. Whatever you square, this point also, if it is a negative or positive value, whatever the square of a positive or a negative value is always going to be positive. So the square of each of these values would be positive. I hope that makes sense. So the current will change very sinusoidally, but I squared is always going to be positive, because square is going to be positive. So as a result, as you can see here, the current is going to be always double the earlier amount. it would have the double the area amount. Now when we vary this current up and down, you can see the frequency doubles at the same time. Frequency doubles at the same time. Write down a note. To figure out how RMS values have a root 2 factor in it, we need to consider the following situation. Leave a line and write. In the equation P equals I squared R explains that power is directly proportional to the square of the current. When taken a current that varies sinusoidally, we will observe that I squared is always positive. And I squared varies at twice the rate as current. I squared varies at twice the rate with current. Please draw this diagram 27.10. And after that write as a result, if we are to obtain the average value of I squared, we see that to be half of the square of the peak current. Half of the square of the peak current. To find the RMS, we need to find its square root. Therefore, we find the root of the mean of the square of the current. We find the root of the mean of the square of the current. Root of the mean of the square of the current. So that is how we get RMS. I hope that makes sense. And then write down underneath that IRMS equals root mean of I squared. So mean is represented by these two signs. So that gives us, so I squared is then half IO squared. Then from that we get IO equals root 2 IRMS. I hope that makes sense. If you understood these things, please refer to all of these things. And if you have understood, well, that's good. If you haven't, please ask questions.